Hello, and welcome to Stat 200. I'm Dr. Zimmerman. I coordinate many of the instructional materials that are used across all online sections of the course. For each lesson, there will be a full video lecture, such as this one. You have the option of watching the video lecture or reading the online notes. Some students also choose to do both. The content covered in the videos and the notes will be the same. The examples, however, will be different. The online notes do tend to have more examples than the videos, so if you're looking for additional examples, check out the online notes. The other major difference between the videos and the online notes is that the videos will not include Minitab Express instructions. The main reason for this is that there are two different versions of Minitab Express, one for Windows and one for Macs, and also the Minitab Express tutorials usually require you to download a file to follow along. So all of the Minitab Express instructions will be in the online notes, usually in their own section towards the end of the lesson. These videos do tend to be long, so I recommend that you take breaks while watching. If you're watching the lecture videos in YouTube, there'll be timestamps in the video's description, which will at least let you fast forward or rewind if there are specific topics that you're looking for. Each video will begin with a list of topics and a brief introduction. These are the topics we'll be covering this week. Lesson 1 is sort of a short crash course in basic research methods. Depending on your academic major, you may also have to take a full course in research methods. Those courses usually focus on the methods specific to your discipline. In this lesson, we'll focus on terminology that's applied across many fields. This lesson is different from almost every other lesson in the course because there are no calculations. There's a lot of vocabulary, so what I recommend is making and studying from flashcards for this specific lesson. Now, let's get started by looking at the first topic here, common terminology. As we talk about research studies in this lesson, there are some terms that will come up often, particularly case and variable. They're probably two of the most frequently used terms in this course. A case is an experimental unit from which data are collected. If we're studying people, the term participants may be used. If we're studying animals, the term subjects is often used. Another synonym is experimental unit. A variable is a characteristic of cases that can take on different values. In other words, it's something that can vary. And a constant is a characteristic that is the same for all cases in a study. In other words, something in a study that does not vary. Let's look at an example. Do Stat 200 students who take the midterm exam on Sunday tend to score higher than students who take the exam on Tuesday? The cases are the students. These are the units from which the data are collected. There are two variables. The first is midterm exam scores, and the second is day of the week. These are both characteristics that vary between students. And a constant in this study is Stat 200 because all students are enrolled in Stat 200. If you'd like to see some additional examples, remember that there are more in the online course notes. The lecture videos can get a bit long, so I usually try to limit myself to just one example per topic in the lecture videos, but there are usually some extra examples in the notes. This brings us to our next topic of reliability and validity. Reliability and validity are terms that are often used in research methods and statistics, and like many of the terms we'll see in this course, their meaning when discussing a research study can be a little bit different from how they're sometimes used in everyday conversation. In statistics, reliability refers to the consistency of the data. For example, if you're at the doctor's office, they sometimes measure your height twice. They should get the same measurement both times. Getting the same measurement each time is an indicator that their measurements are reliable. In other fields, such as educational and psychological testing, reliability may be evaluated by examining the internal consistency of a test or survey. In other words, the degree to which all the questions on the test or survey are correlated with one another. Validity is the extent to which data measure what they are reported to measure. Data are valid if they're really measuring what the researchers are claiming to measure. There are many different ways to evaluate validity. For example, types of criterion-related validity are assessed by examining how the data are related to other data. A measure should be positively correlated with other measures that are theoretically similar and not correlated with measures that are not theoretically similar. Reliability and validity are often depicted using dartboards. On the left, all of the darts are in the center. They're reliable because they're all close together, and they're valid because they're all at the center. In the middle dartboard, all of the darts are together, so they're reliable, but they're not near the center, so they're not valid. In other words, they're consistently wrong. And in the last dartboard, the darts are all spread out. Most aren't near the center, so these are neither reliable nor valid. Reliability is a prerequisite for validity. In other words, a measure cannot be valid unless it's reliable. Our third topic is levels of measurement. This is one of the most important topics in Lesson 1 because in all of the remaining lessons, you'll need to be able to identify the level of measurement of a variable. We have two different classification methods. The first, shown here, has 4 levels: nominal, ordinal, interval, and ratio. As we move from left to right, the qualities that need to be present increase. A nominal level variable is going to be categories. These have no meaningful order of magnitude. In other words, there's no ranking. Common examples include biological sex, ethnicity, and academic major. Next, we have ordinal level variables. These variables are still categories, but they do have a meaningful order. What distinguishes ordinal from interval is that ordinal level variables do not need to have equal intervals. The most common example is rankings. For example, finishing place in a race. The first place finisher is better than the second place finisher, but the difference between first and second place may not be the same as the difference between second and third place. Both nominal and ordinal variables fall under this umbrella of categorical variables. The third variable type is interval level. These are variables that are measured as numerical values with equal intervals, but no absolute zero. So going from ordinal to interval, we've added the additional quality of having equal intervals. An absolute zero means that there is an observed value of 0 that symbolizes a total lack of the characteristic. In other words, 0 really translates to nothing. An example of an interval level variable is temperature in degrees Fahrenheit. This variable takes on numerical values that have equal intervals, but it does not have an absolute 0. A temperature of 0 degrees Fahrenheit is really cold, but it doesn't mean that there's no temperature. Without an absolute 0, this is an interval level variable. And finally, ratio level variables are numerical values with equal intervals and an absolute 0. An example could be distance run. If you've run 0 miles today, then you have not run. In other words, a value of 0 communicates that you have done no running. Both interval and ratio level variables fall under this umbrella of quantitative variables. Most of the time, we'll use the categorical and quantitative classifications. For the most part, the graphs and analyses that we use for interval and ratio level variables are the same, but there are a few differences for nominal and ordinal level variables, so it's important for you to know both classification systems. Our next topic this week is independent and dependent variables. In some research studies, one variable is used to predict or explain differences in another variable. In those cases, the independent variable is used to predict or explain differences in the dependent variable. The independent variable is also known as the explanatory variable, predictor variable, or X variable. Later in this lesson, we'll learn about experimental studies. In an experimental study, the independent variable is the variable manipulated by the researcher. The different values of the independent variable are then referred to as levels of the independent variable. The dependent variable is also known as the response variable, outcome variable, or Y variable. This is the variable that's being predicted in an experimental study. Let's look at one example. Can homework scores be used to predict midterm exam scores? Here, we do have a situation where one variable is being used to predict the other variable. Homework scores are being used to predict midterm exam scores. So homework scores are the independent variable and midterm exam scores are the dependent variable. It's important to note that in some non-experimental research studies, these classifications will not apply. For example, if we're looking at the relationship between two variables like height and weight, but we're not interested in which one is causing changes in the other, in that situation, we wouldn't need to classify the variables as independent and dependent. We would just be looking for an association or a correlation between the two. The methods we'll be covering in this course can be classified as descriptive or inferential. Descriptive statistics are values or procedures used to summarize data. These include numerical values like a proportion or an average, or it also includes most types of graphs. Inferential statistics are procedures that use data from a sample to make a conclusion about the population. Which brings in two more new terms, population and sample. The population is the entire set of possible cases. So this is every single individual that we would like to know something about. And the sample is a subset of the population from which data are collected. One last piece of terminology here, when we describe data, so when we're computing descriptive statistics, values concerning a sample are referred to as sample statistics, while values concerning a population are referred to as population parameters. So throughout the course, you'll hear me use terms such as statistics and parameter. Remember that a statistic is a value describing a sample, and a parameter is a value describing a population. We often have questions concerning populations, but gathering information from an entire population is not always possible due to barriers such as time, accessibility, or cost. So instead of gathering information from the whole population, we usually just gather data from a smaller sample. And then we analyze those sample data and use inferential methods to make a conclusion about the bigger population. Let's look at a quick animation that demonstrates this inferential process. This is the population. In other words, these are all of the people that we would like to know something about. For example, maybe we want to know their average age, or we may want to know their opinion on some topic. Populations are often very large and inaccessible, but we can use sampling methods, which we'll learn about in more detail later in this lesson, to select a subset of the population to study. That subset is known as the sample. Then we can use inferential procedures, which allow us to use those sample data to make a conclusion about the larger population. These are some examples of the descriptive and inferential methods that we'll be covering in this course. In lessons 2 and 3, we'll focus on descriptive statistics, and in lessons 4 through 12, we'll work primarily with these inferential statistics. The next 4 topics that I'll cover all fall under the category of research study design. Some of the methods used can vary between disciplines. In this section, we'll learn about some of the common aspects of research study design that are applied across most disciplines. Depending on your academic major, you may have to take a research methods course, and that should go into much more detail and focus on the methods used in your specific discipline. We'll start by distinguishing between experimental and observational designs. An experimental study is a study in which the researcher manipulates the treatments, in other words, levels of the independent variable, received by the cases before collecting data. This is also known as a scientific study. An observational study is a study in which the researcher collects data without performing any manipulations, also known as a non-experimental study. So if we compare these two, the difference is that in the experimental study, the researcher has control over which level of the independent variable each case receives. And in an observational study, they're going in and they're just observing perhaps pre-existing groups or just variables that are naturally occurring. Let's look at a couple examples. Here's a research question. Can homework scores be used to predict midterm exam scores? An instructor collects data from their gradebook at the end of the semester. We saw this example earlier. We said that homework scores were the independent variable and midterm exam scores were the dependent variable. In an experimental study, the researcher manipulates the level of the independent variable. That did not occur in this case. It's not possible for the instructor to assign students to have different homework scores, so this is an observational study. And one more example. Patients are randomly assigned to receive either treatment A or treatment B. After the treatment, their resting heart rates are compared. Here, the independent variable is the treatment and the dependent variable is the resting heart rate. The researcher is assigning participants to different levels of that independent variable. Note that they randomly assigned some to treatment A and others to treatment B. So this is an experimental study. Usually, if there's an option available, experimental studies are preferred over observational studies because things like randomization, placebos, and blinding, which we'll learn about later in this lesson, can be built into an experimental design, but not an observational design. And all of these things can strengthen the conclusions that can be made at the end of the study. For example, causal conclusions cannot be made from an observational study. They can be made from a well-designed experimental study. But there are times when an experimental design is not possible. If the independent variable is naturally occurring, it may not be possible for the researcher to manipulate it. For example, race, ethnicity, birthplace, age, gender identity, and biological sex are variables that can't be randomly assigned to different cases. I just mentioned that causal conclusions cannot be made from an observational study, but they can be made from a well-designed experimental study. In statistics, causation occurs when changes in one variable can be attributed to changes in another variable, which is in contrast to an association, which is a relationship between variables with no implied causal direction. In order to make a causal conclusion, you need to have an experimental design in which cases are randomly assigned to levels of the independent variable. Randomization is the term that we use to describe that random assignment of cases to different levels of the independent variable. An experimental study with randomization will sometimes be referred to as a randomized experiment. In a randomized experiment, we can conclude that differences in the independent variable are causing differences in the dependent variable. A common problem in studies without randomization is that there may be other variables influencing the results. These are known as confounding variables. A confounding variable is a characteristic that varies between cases and is related to both the independent and dependent variables. It's also known as a lurking variable or a third variable. Let's look at an example of how these concepts could be applied. Here's a research question. Do students who use tutor.com have different midterm exam scores than students who do not use tutor.com? First, we have an observational design. The midterm exam scores of students who use tutor.com and do not use tutor.com by their own choice are compared. Because this is an observational study, there is no randomization, which means no causal conclusion can be made here. We can conclude an association, but from this design, we cannot conclude that using tutor.com causes differences in exam scores because the students are self-selecting to either use or not use tutor.com. There are likely some differences between the two groups other than just the tutor.com usage. Those differences are the confounding variables. They could include employment status. If we find that students who are working full-time are less likely to use tutor.com than students who are working part-time or who are not working. Prior knowledge of statistics, because students with lower prior knowledge may be more likely to need help. Students with really high prior knowledge may not have any questions and may not need tutoring. Or caregiver status. For example, students who have children or who are caring for a family member, that could impact the time that they're available to seek out services such as tutor.com. Because of these confounding variables, the two groups that we want to compare may be different at the beginning of the study. If we find any differences between the two groups, we don't know if it's because of their tutor.com usage or because of one of these other confounding variables. In order to make a causal conclusion, we should use a randomized experimental design. In this design, each student is randomly assigned to either use tutor.com weekly or to never use tutor.com. Because students are randomly assigned to levels of the independent variable, we can make a causal conclusion here. All of the confounding variables we saw with the observational study are now randomly split between the two groups with the randomization. If any differences are observed between the two groups, with this design, we can attribute those differences to the independent variable. Control groups are another aspect of research study design that are often included to strengthen the conclusions that can be made. A control group is a level of the independent variable that serves as a baseline or comparison group. They may receive the current standard treatment, no treatment, or a placebo. A placebo is something that appears to be a treatment but actually is neutral and does not contain any active ingredients. For example, a placebo pill is a sugar pill given in a medication study. A placebo can lead to the psychological phenomenon called the placebo effect, which occurs when participants are given placebo treatment and they feel like they've experienced a change even though they're not receiving any actual treatment. Let's look at an example. Researchers are studying the impact of caffeine on typing speed. They are comparing three groups: regular coffee, decaffeinated coffee, and no coffee. The group that receives the regular coffee is the treatment group. Of the three groups, this is the only one that will actually consume caffeine. The group that receives the decaffeinated coffee is the control group. Assuming that they're not told that this is decaf, I would also consider them to be a placebo group because they're drinking something that looks like regular coffee but doesn't contain caffeine. And the group that is given no coffee is another control group. When including a placebo condition in a research study, it is usually necessary to incorporate blinding. Blinding is a procedure employed in research in which the participants and/or the researchers interacting with the participants do not know which treatment each case is receiving. A study can be single-blind or double-blind. A single-blind study is a research study in which the participants do not know the treatment group that they've been assigned to. And a double-blind study is a research study in which neither the participants nor the researchers interacting with them know which cases have been assigned to which treatment groups. If we look at the previous example, where the researchers were comparing three groups in terms of their typing speeds, this would be a single-blind study if the participants did not know which group they were in, So they didn't know if their coffee had caffeine in it or not, or for the no coffee group, they didn't know that there were other groups that did get coffee. But in a single blind study, the researchers who are interacting with the participants do know which participants are in which groups. So the researchers who are giving them their beverages and guiding them through the study would know which of these three groups each participant was in. In a double-blind study, neither the participants nor the researchers who are interacting with them know who's in each group. Someone on the research team would have a list of who is in each group because they would have to set up the cups of coffee, but that person would not be the one directly interacting with the participants. The people directly interacting with the participants would have no idea which cups had caffeine and which cups didn't. Whether blinding is necessary or not, and if it is, which type is needed, depends on the research study. If the study involves a placebo, then you probably want the participants at least to be blinded. If there's a chance that the researchers could influence the participants' reactions, or if the researchers are collecting some subjective data where they could be biased, then the researchers should probably also be blinded. The last concept that falls under the umbrella of research study design that we're going to cover is independent and paired samples. In an independent samples design, the data from each group are not related in any way. Well, in a paired samples design, the data from each group are in some way matched or paired together. For example, we could study parent-child pairs or husband-wife pairs. The most common paired samples design, though, is the repeated measures design. This is a design in which the dependent variable is measured for every case in every level of the independent variable. For example, a pre-test, post-test design, which is where the dependent variable is measured before and after treatment for all cases. Let's look at some examples. The first example is an independent samples design. We want to know, on average, can cats run faster than dogs? We take a sample of cats, and then we take a sample of dogs. The two groups are in no way matched or paired. The cats in the first group and the dogs in the second group have no one-to-one relationship, which means that these samples are independent. The second example we'll look at is a paired samples example. I purposely chose an example here that is not repeated measures because we'll see repeated measures in the next example. Here, in newborn fraternal twin pairs consisting of a male and a female, do males tend to weigh more than females at birth? We have two groups again, babies assigned male at birth and the babies assigned female at birth. But this time the two groups are paired because we're looking at newborn fraternal twin pairings consisting of a male and a female. For each case, in the male sample, there's a corresponding case in the female sample. The reason why we would use a paired samples design like this is that it could help control for some other variables. In this particular example, since we're working with newborn twins, this method could control for things like mother's diet or whether they were born full term or premature. The last example I'll show you is a repeated measures example. This is a specific type of paired samples design where the same case is measured at every level of the independent variable. Here's our research question. Do students tend to have faster heart rates at the beginning or end of an exam? Data were collected from the same students before and after an exam. Again, we have two groups, before the exam and after the exam. In this study, the same students are having their heart rates measured twice, before and after. Because the same students are measured twice, this is a repeated measures design. This brings us to sampling methods. There are many different ways to select a sample from a population. Some methods are random and based on probabilities, while others are not. Typically, probability-based methods are preferred because they result in representative samples. A representative sample is a subset of the population from which data are collected that accurately reflects the population. In other words, it's a sample that reflects the intended population. The most common probability-based sampling method is simple random sampling. This is a method of obtaining a sample from a population in which every member of the population has an equal chance of being selected. For example, if there are 500 students in Stat 200 this semester, and I'd like to interview a simple random sample of 10 students, if I had a list of all 500 names, I could use a random number generator function in Excel, or Minitab Express has a sample from columns option. I could also print out all of their names, cut them into equally sized pieces, and pull 10 names out of a hat. With any of these methods, each of the 500 students has an equal chance of being selected to participate in the study. Using simple random sampling, cases are selected from the population without replacement. This means once a case has been selected to be part of the sample, it cannot be selected a second time. There are many other probability-based sampling methods. Simple random sampling is the most basic. Some more advanced probability-based methods that you might see if you take a research methods course include cluster sampling or stratified sampling. While probability-based sampling methods, such as simple random sampling, are usually considered to be better because they produce a sample that is representative of the population, there are times when it is not possible to use these methods. For example, researchers often don't have access to the entire population. Or if the research study has some risks, it may be more ethical to only study volunteers. In cases where probability-based sampling methods are not practical, convenience sampling methods are often used. Convenience sampling is a non-random method of obtaining a sample from a population by ease of accessibility. For example, posting a call for volunteers on a site like Facebook or LinkedIn. Convenience sampling methods are usually the easiest, but the downside is that the sample may not be representative of the intended population. This brings us to the last concept we're going to cover this week, bias. This is another term that may have a slightly different meaning in statistics. In statistics, the term bias means systematic favoring of certain outcomes. Bias can be an underestimate or overestimate caused by poor data collection methods. These are not differences caused by random sampling variation, and they're not differences that actually exist in the population. There are many different types of bias. In this course, we're just going to focus on 3 that are relatively common across most fields. The first is sampling bias. This is a systematic favoring of certain outcomes due to the methods employed to obtain the sample. For example, on the last slide, we learned that convenience sampling approaches may produce samples that are not representative of the intended population. That's an example of sampling bias. Next is non-response bias. This is systematic favoring of certain outcomes that occurs when the individuals who choose to participate in a study differ from the individuals who decline to participate. And finally, response bias, which is the systematic favoring of certain outcomes that occurs when participants do not respond truthfully. You see this a lot when people are asked really personal questions. They may lie a little bit or they may lie a lot because they're embarrassed or because they want to appease the researcher. Students often get non-response and response bias flip-flopped. In non-response bias, the problem is that people aren't participating. In response bias, they're participating, but they're not being truthful. That concludes all of the topics in Lesson 1. except for using Minitab Express to obtain simple random samples. Remember, all of the Minitab Express instruction you're going to find in the online notes. For this lesson, and for most lessons, the Minitab Express guides will be towards the end of the lesson. There's usually a file for you to download and instructions and videos for both the Windows and Mac versions. Lesson 1 is different from most of the remaining lessons in that it does emphasize a lot of vocabulary. Starting with Lesson 2, we'll start to see more procedures, which is where I think the videos become a bit more engaging and useful. If you have any questions after watching this video and reviewing the online notes, please post them to the Lesson 1 discussion board in your section of the course in Canvas.